In 2017, the Obervermuntwerk II major project in the Silveretta entered its fourth year of construction, indicating that the construction work is nearing completion. Significant progress was made in various construction phases this year. In the machine cavern, a massive cavity 800 meters deep in the mountain, concrete work is mostly completed. Turbines and pump spirals are partially embedded in concrete, and teams are primarily focused on water jetting. In the underwater section, sluice boxes have been installed, and the concrete construction in the machine cavern and the adjacent transformer cavern was mostly finished by the end of 2016. In the 2.8-kilometer-long Silveretta Tunnel, continuous efforts were made on the concrete lining, with excavation completed in 2016. The inner shell was then concreted, using pre-made concrete parts called tubinger. Progress was made section by section, with a massive formwork carriage advancing 14 meters at a time serving as a mold for the concrete lining. The adaptation of the lining to the mountain's contours was done locally, requiring approximately 220 cubic meters of concrete for each section. Overall, around 45,000 cubic meters of concrete were used in the Silveretta Tunnel. One of the most challenging tasks was completing the area where the connecting tunnel branches off to the water castle from the Silveretta Tunnel. Here, intricate reinforcement work was necessary. At the lower end of pressure board 18, the installation of the distribution pipeline, known as the hose pipe, with one inlet and two outlets, began by the end of 2016. The armor was assembled from individual parts, transported here and then welded together short by short. The workers spent 5 months transporting, attaching and welding the pipe parts for the distribution pipeline. The final major pipe short took place on January 25, 2017, and this part will no longer be visible in the future, as it is concealed behind a meter-thick concrete layer. Significant progress was also made in the water castle, whose shaft was completed in 2016. Concrete injections started in both the water castle chambers and the water castle shaft to fill the smallest cavities between the rocks and the concrete lining, ensuring the highest possible stability of the entire system. While steel, water, and concrete workers were still active on the construction site, parts for the new power plant were already being manufactured in various locations along the Alps and slightly beyond. The light blades for the turbine were produced in Ravensburg near Lake Constance, and the pump impeller was processed at Voith in St. Polten. The pump's hull was welded together at the same location, and parts of the converter were also created here, combining large-scale engineering with fine craftsmanship. In St. Polten, the connection piece between the pump and the underwater attachment, known as the Krimmer attachment, was also produced at Ford. All these parts were meticulously checked for dimensional accuracy and material quality during production, as they must later withstand immense forces. The individual parts were assembled in the factory and checked for dimensional accuracy, such as the converter that will later connect points and the generator. While some parts will be disassembled and only reassembled on-site, others, like this pump cover, will be delivered fully assembled. Moving to Switzerland, in the canton of Aargau, at General Electric, parts of the generator for the Obervermuntwerk II are already being manufactured. Before assembling the fixed part of the generator, around 108,000 individual sheets, each weighing 150 tons, are manually inserted. The sheet package is then permeated by a rotating magnetic field generated by the rotating poles during operation. The sheets are layered regularly during the process, compressed at intervals. Also, the majority of the conductors, referred to as bars in technical jargon, are already installed at the manufacturer's site to avoid any delays on the construction site. A total of 528 copper bars, where electrical energy will be generated later, are inserted and screwed here. However, they also need to be soldered and well insulated against high electrical voltages to prevent short circuits within the system. After completion, the stator must be disassembled into two parts due to its weight and dimensions. Otherwise, it could not be transported on the roads to the construction site. While some parts will be disassembled and only reassembled on-site, others, like this pump cover, will be delivered fully assembled. Moving to Switzerland, in the canton of Aargau, at General Electric, parts of the generator for the Obervermuntwerk II are already being manufactured. Before assembling the fixed part of the generator, around 108,000 individual sheets, each weighing 150 tons, are manually inserted. The sheet package is then permeated by a rotating magnetic field generated by the rotating poles during operation. The sheets are layered regularly during the process, compressed at intervals. Also, the majority of the conductors, referred to as bars in technical jargon, are already installed at the manufacturer's site to avoid any delays on the construction site. A total of 528 copper bars, where electrical energy will be generated later, are inserted and screwed here. However, they also need to be soldered and well insulated against high electrical voltages to prevent short circuits within the system. After completion, the stator must be disassembled into two parts due to its weight and dimensions. Otherwise, it could not be transported on the roads to the construction site. A total of 28 such poles are manufactured here, 14 poles per machine. Considerable manual labor is also required in the construction of transformers at Siemens in Linz. Since 1920, transformers have been custom-made at the Linz site. For the Obervermuntwerk II, two machine transformers with a capacity of 200 megawatt-ampere were manufactured. In the first step, the coils are wound, and the transformer core is manually stacked from thousands of individual sheets. Finally, the individual parts of the active part are assembled and lifted into the transformer vessel using a crane. The transformers, weighing 152 tons each in an empty state without oil, are the heaviest individual components transported to the construction site. Extensive tests are conducted in the workshop before shipping. Next is Kaisast, near Basel in Switzerland, where Moser Glaser manufactures the bus bars. The connection between the generator and transformer. The aluminum conductors must first be bent to fit the future course in the cavern. Since the bus bar will transport electrical energy with a voltage of 14,000 volts and several thousand amperes during operation, it must be insulated in layers. Pieces are welded to the ends of each bus bar, and of course each bar is individually tested thoroughly. Like all other mechanical and electrical components, the bus bars are delivered to Silveretta weeks later and assembled piece by piece in the upper part of the cavern to establish the connection between generators and machine transformers in the transformer cavern. Meanwhile, in another part of the cavern, the last concrete work is underway, and the final foundations for the machines are being created, each containing concrete pedestals and supply lines. Then arrives the first significant machine part, Part 1 of the generator side cover of the pump. Once again, the foresight in planning the construction is evident, as the cover had to be hoisted to a construction site where the already embedded spiral is located, so that it cannot hang directly under the crane's self-driver is reloaded. The transport from the Kops Werk II to the cavern of the Obervermuntwerk II takes between 5 and 6 hours. However, public traffic on the Silveretta High Alpine Road is hardly affected, thanks to bypasses and parking spaces. Even during unloading, precision is crucial, as the building was constructed exactly high enough for half of the stator to be lifted over the embedded spirals. Hours later, the enormous part is in its designated location, fitted into prepared brackets and screwed in. The most elaborate transport is yet to come. The first of the 152-ton transformers is delivered from Linz to Montafon with a special train due to its high transport weight. At the Rotunde work, it is transferred to a low loader and taken to the Kops Werk II in Partenen at night. From there, the self-driver ascends the many turns to the Verbonsee and into the cavern of the Obervermuntwerk II. The self-driver starts at night to minimize traffic disruption, since this transport, along with the vehicle itself, weighs around 40 tons, totaling nearly 200 tons. The transformer is approximately 7 meters in length, 3.5 meters in width, and about 4.5 meters in height. The operating crew of the self-driver is primarily on foot along the entire route. Shifting the transformer upon arrival at the power plant, from the entrance area to the transformer cavern, is challenging. There is no crane at its destination to lift it from the vehicle. Therefore it has to be placed on transport rollers in the large machine cavern and then pushed or pulled with gripping tugs into the transformer cavern. The movement is facilitated on embedded steel rails, planned and installed early during the concrete works. Transformers convert the energy provided by the power plant for the high-voltage grid or absorbed from the grid to the respective voltage level. For the generators in the power plant, this is 14,000 volts, and in the lines up to the Burs substation, it is 220,000 volts. However, the transformer is far from finished, as many components, such as the cooling system lines, expansion vessel, and isolators, can only be mounted now to avoid making the transformer too large for transport. Finally, 36,000 liters of special insulating oil are filled in, warming the transformer oil to facilitate easy pouring into the transformer. The transformer now weighs a total of 187 tons. Progress is also evident in the assembly of the 4 ball valves. They are each screwed to the flanges of the distribution pipeline, secured with bolts weighing 40 kilograms each. Now, 2 lifting cylinders are attached to each ball valve, allowing the ball to be opened or closed within the casing. These arms, with their weights of up to 80 tons, serve as an important emergency measure. If there is a failure, they gradually close the pressure pipeline with their own weight. Each of the 300-ton ball valves begins to move during the initial tests, initially very slowly, until all endpoints are adjusted. The rotor's individual parts are assembled in the cavern. First, the rotor central body must be rotated using a telehandler and the haul crane. The rotor central body must not touch the ground during this process to prevent any damage, requiring absolute precision from both crane operators. The 2 shaft pieces, manufactured in Italy, are first screwed to the rotor central body. Only then can the entire part be lifted into the lower stator half. Both haul cranes are needed for transport, as the weight of the entire rotor central body exceeds the maximum load of a single crane, which is 180 tons. One of the next steps is the installation of the 14 poles. The insertion of the poles, with only a 1 mm tolerance, is a demanding process. The poles must be perfectly aligned horizontally and brought to the correct height for installation. The poles now slide one by one into the rotor central body, where they are centrally aligned, wedged, and screwed. The finished rotor can be manually rotated for the first time, allowing checks on factors such as concentricity. Work is also progressing on the underwater side of the machines. The 3.8 meter wide and 58 meter high sluice panels are lifted into their guides in a complex assembly process. These sluice panels, along with the upper waterside ball valves, will later allow the machine to be drained for regular maintenance and inspections. After final assembly, the sluice panels are connected to the control system and checked for functionality to ensure no water can enter after closing. The last hydraulic section completed in 2017 is the underwater connection of the machines in the cavern with the Vermont Sea. This section is also lined with concrete. Creating the junction to the access tunnel involved using a special 3-part wooden formwork that had to be tightened over the previously installed reinforcement. The final connection piece is a roughly 14-meter-long pipe, allowing access for inspections. On November 27, 2017, the underwater area was filled for the first time with water from the Vermont Sea, done slowly with pumps while continuously checking for leaks and ensuring pressure resistance. Pride rests with the lower part of the S-boards, particularly below the junction to the water castle, where steel armoring, up to 14 meter long, was mounted over several months in the 4th year of construction. The inner diameter of the pressure pipeline decreases, and the wall thickness increases to withstand the tremendous water pressure. The armored section of the pressure tunnel ends in the expansion niche, where the end of the pipeline is flanged. Expansion pipes will be installed between the armor of the pressure tunnel and the already completed pressure shaft, allowing inspection access during the operational life of the Obervermuntwerk II. Work has also begun on the portal structure in the outdoor area of the power plant. This building below the dam of the Verbundsee will be one of the few visible parts of the Obervermuntwerk II from the outside. Since the start of construction in the spring of 2014, the construction consortium has spent 1.5 million working hours on the project until the end of November 2017. Since the beginning of the year, the electricians have been working in the cavern, and by mid-June, the 20 kilovolt system responsible for the power plant's own needs was commissioned. Prefabricated control cabinets are gradually being installed, connected and commissioned, followed by extensive tests and functional simulations of individual systems. Due to the limited space in the cavern, an encapsulated gas-insulated 220,000-volt SF6 switchgear is used for energy transport, which is largely completed. The special insulating gas, sulfur hexafluoride, reduces the dimensions of the switchgear and aids in arc extinguishing during switching operations. The generated power is transported to the high-voltage grid from here. The power transmission takes place through the Promenierstein, where the high-voltage cables previously installed in the fall of 2016 are now connected in the cable junctions. The high-voltage line is led down the route of the former inclined elevator of the Verbundwerk into the valley. Here, the cables are pulled even in extremely harsh weather conditions. Time is of the essence, as work cannot be carried out in steep terrain during snow. 3 cables, each with a diameter of 13.2 centimeters and a total length of about 4.9 kilometers, are laid from the 220 kilovolt switchgear in the cavern to the outdoor switchgear Kopse-Platte in the valley. The exposed sections in the steep stretch where the cables lie are covered, and later greened to preserve the landscape and wildlife. The completion of the cable and escape tunnel, with the aid of push devices and winches, to the 220 kilovolt switchgear is underway. In the machine cavern, the completion of the first set of machines is progressing rapidly. The upper stator half, weighing 112 tons, is now placed on the lower stator half and bolted together, with the movable rotor in between. In the transition area between the two halves, the bars still need to be soldered and insulated. The general assembly is completed with the high-voltage test on both machines. Intensive work is being carried out on both machines, with all components gradually arriving. The Francis turbine runner is being installed, and due to limited space between the individual parts, the assembly poses a special challenge for the technicians. An assembly facility specially designed for this construction site is used to precisely fit and screw the components. It won't be long until the runner turns for the first time, marking another step towards the completion of the turbine. The installation of the guide vanes, manufactured in Ravensburg, is another crucial step. The 20 guide vanes will control the water flow on the runner, regulating the power. They are bolted and connected to the control mechanism. The heart of the pump, the impeller, is now being installed. The special crane hook is used again to insert the impeller into the already embedded spiral. The impeller, with a diameter of 3.4 meters and a weight of 19 tons, is one of the largest individual parts of the machine set, and precision is crucial for its exact installation. The final major part of the machine, the pump cover, is then installed. Unlike the turbine, the guide vanes were already assembled with the impeller in the factory, allowing the pump cover to be bolted as a complete unit to the machine set. Screws and nuts are once again used, exceeding normal dimensions. Overall, the Obervermuntwerk II project has come significantly closer to completion in its fourth year of construction. In some areas, such as the portal and ventilation structure of the water castle, the condition has already reached the anticipated state post-completion. In the cavern, the machine's sluice valves, expansion pipes, control technology and much more have been assembled to the extent that the runners are already turning. Soon, they will no longer be visible, as commissioning work on the machine set will begin in a few months, allowing the power plant to commence operations by the end of 2018. The workers, technicians and engineers from the contracted companies and Vorarlberger Illwerk KG have once again done an excellent job in the fourth year to achieve the ambitious goal of preparing the entire power plant for operation in just over 4 years.